Welcome, everybody in the lecture hall. Welcome, everybody on Zoom. Welcome, everybody watching us from the future. Today, we are going to compress data and to squeeze as much data as we can in as little space as possible. And when I mean data, I mean more exactly the standard inverted index. So I told you last time about the Heap's law and the Zipf's law. The Heap's law basically says that if you keep adding more and more documents and more tokens to your collection, then the number of terms grows in the square root of the size of the collection, right? So the number of terms, that's basically the height of the standard inverted index. That's how many terms you have in the vocabulary and in the dictionary structure. And Zipf's law says that the collection frequencies drop in 1 over x. So if you take the ranking, if you look at the number of times that each term appears in the collection, and you sort them by decreasing collection frequency, then it's a hyperbole. It's 1 over x up to a constant factor. So that's Zipf's law. And this is where I left you last time. And now we are going to move on and actually compress some of the structures, starting with the dictionary. So I'm going to start with this part of the standard inverted index. And then in the second part of the lecture, probably also today, we are going to compress the postings and the posting lists. Just a moment, I might need to adjust something. All right. Okay. So we are going to compress the dictionary. So the status quo, what I showed you is that the dictionary is stored as, for example, a B+ tree, could be a hash and so on, but B+ trees allow us to have ranges and support range queries. So we basically have all of these non-terminal nodes, right, with a certain number of keys, and then we have the children, and there's one more child than the number of keys, right? So if you have 3 values, then you have 4 children. And we saw that the size of the B+ trees enforces some interval of number of children, right? For example, between 4 and 7 children per node, right? Speaking of which, just to make sure that you've been following, how many terms can a 4-7 B+ tree of height 3 contain at least? 27, 48, 64, or 96? There's probably one metallic object somewhere. That's where the reflection comes from. Could it be otherwise here? Ah, that's took care of it, almost. It's here. This is... Yeah, maybe this is it, yeah. It's 4 answers so far. Okay, so let's see if you've been answering. Okay, so now it's very strange because the correct answer is 96. So let me explain. 4-7 B+ tree means that we can have between 4 and 7 children, right, per node, except for the root. The root can have less, can have 2. If there are at least 4 children per node, how many values are there per node? Do you remember that? So it's one less, right? If you have 4 children, then you have 3 values in the middle. It's because it's in between the pointers to the children. So between 4 and 7 children means between 3 and 6 values, right? You just need to offset by 1. So now we are looking at the minimum number of terms that we have to have in such a 4-7 b + 3 of height 3. So height 3 means that we have the root, then we have a first layer, then we have a second layer, and then we have the third layer that has all of the actual terms, right? Because in a b + 3, the terms are at the leaves. Now, we can have at least 2 children of the root. Do you agree? The root is the only one that has the right to have less than 4 children. So, but it still has to be at least 2, right? Because if there's only 1, then the root is useless. Then it means it's not height 3, it's height 2, if the root has only 1 child. Do you agree with that? Right? So the less we can expect from the root is to have 2. The least is 2 children. Then the next layer, since it's no longer the root, it needs to have, again, at least 4 children every time. So we are already at 2 times 4. That's 8 on the on the next level. Then we have to multiply again by 4 for the next level. 2 times 4, 8 times 4, 32. And then, so that's the total number of nodes that we have on the third layer, because we're already on the third layer. 2 first layer times 4 second layer times 4 third layer. So we have 32 nodes. How many values at least per node? 3, right? Because it's 4, 7, so it's between 3 and 6. So it's at least 3. So 32 times 3 gives us 96. Who agrees? Right? So it's 2 times 4 times 4 times 3. Okay? So there's 2 things to remember here. It's that the root can have less than 4, and that's the number of values is 1 less than the number of children. So that's 3. Okay, so I just wanted to check on that, but the good exercise was worth it. Okay. But now I'm closing the parentheses and getting back to where we were. So we would like to ideally make all of that fit in the RAM. And I mean mostly this part right here that I'd like to compress. So now, if we look at a fixed length, let's say, for the terms, because we need to store the terms somewhere, right? So these are strings. So imagine that we have a fixed length, 20 bytes. That's reasonable for many words. It's not perfect because you have words like supercalifragilisticexpialidocious that don't fit in there. So that's kind of the problem. But still, let's assume that for the purpose of computing some stuff. So then the size that we would need is 20 bytes for every term. Then we need 4 bytes, that's 32 bits for the pointer, for the document frequency. Remember these purple places. And then we need 4 bytes. That would be the pointer to the postings list, right? So we have the document frequency, the pointers to the posting list. And the posting list, I don't care about them just yet, right? So I'm just keeping them out of the picture. So basically, if you add everything, that's 20 plus 4 plus 4, right, per term. Then you multiply with the number of terms. But we can actually fix that, because this is not great for 2 reasons. First, because there are words that are not going to fit completely in there, which can be a problem. You could still group them in some bucket and so on, but still not satisfactory. But here, it's even worse. Here, we're wasting space because we're allocating 20 bytes, 20 characters, and we are wasting a lot of space in there, right? So this is not good. What if we could make it dynamic, right? That I exactly allocate the exact number of characters that a word has. To simplify things, I'm considering just ASCII, but we need to adapt to UTF-8. But the problem you have is that in that case, if you do allocate exactly the proper number of characters for every term, then you need pointers to keep track of where the words begin and where they end, right? If we allocated exactly 20 bytes for every term, then that's easy. It's just pointer arithmetics, and you can locate any term, and you know exactly when they start and where they stop. But since now we dynamically allocate exactly the right number of bytes, then we need additional pointers. Maybe we don't need 4 bytes, so let's try to really squeeze. I'm not sure how on the hardware you will manage to do that, but let's say we have 3 bytes in there to point to the beginning and start of the words. So it's 2 to the power of 24, so that's 16 million, right? Possible addresses with 3 bytes, which is reasonable because that's the number of terms, the order of magnitude of the number of terms scales in the square root. So that sounds like a reasonable assumption. And then we have here the average size of the average length of a term. And that you can compute for an average. If you look at terms in real life, you can basically have an average of 8 bytes. That's just an average. So now we have 4 plus 4 plus 3 for the pointers to the start and end of the terms, plus 8 bytes on average per term. So now you see we did better than the 20, because now we've replaced the 20 with 3 plus 8, right? So that's already some compression, right, that we managed to squeeze a bit more. Now, we can squeeze a little bit more than that by trying to have even less pointers, meaning that instead of pointing to every single term that there is, and I have a pointer every time, what I can do instead is skip some of them and say that every k terms I have a pointer, but it means that I still need to know in the middle of that when they stop, because in that example, I have 3 terms in between pointers, so I know where this triple of terms is starting and when it ends. Then I know when this triplet of terms starts and ends, but I still need to know here when the individual words or terms start and end, right? Because the pointers, now I have less of them, so I no longer have a pointer here, and I no longer have a pointer there. And that is solved with the blue numbers that you see here, the blue numbers, that give you the length. So here you basically have a pointer that arrives here. Then you know there is a term that follows with 8 characters. Then you have 3, so there is a term with 3 characters. And then there is 4, so there is a term with 4 characters, right? And I don't know what my computer is doing, but anyway. Sorry? Oh, it's also on Zim, okay. So anyway, since we have a pointer every k terms, we need to add 1 more byte in here. I think 1 byte should be more than enough to cover the length of a term. 1 byte, that's 8 bits, so that's 256. I don't think we'll find a term that has more than 256 characters, so not even supercalifragilisticexpialidocious. So that should be enough. So we add 1 term. How do you see that? It's no longer 8 here, it's 9, right? 9 bytes on average per term. But what I get from adding that byte in here is that now I have 3 divided by k here. So I'm able to reduce that size. All right, who is following? Right, so these are just ways to squeeze. Of course, it's getting very low level right now to manage to squeeze all that. But now I have something even better than that. I wanted to say before, oh no, let me tell you the one thing even better than that, because I don't want to interrupt the flow. If you want something even better than that, you start by noticing that the terms are sorted alphabetically, right? So if you have that latest technique I showed you, you're going to have the length here, and then a word, and then the length, and then a word. But since it's alphabetically sorted, you notice what's happening here. I basically have repeated patterns, right? Automata, automate, automatic, and automation. And here again, you feel like maybe we can compress that even more, right? Like this. And indeed we can. That's called front coding. What we can do is add a special character here that basically says whatever is on the left is shared by the next terms. And then we have automata, automate, automatic, automation, and so on. So with special characters, because it's sorted alphabetically, and there will be patterns like that, we can squeeze even more with front coding, right? So this is the fourth technique. And if you summarize all of these four techniques in terms of the effect they have, that would be with the fixed width. So if you really allocate 20 bytes for every term, it takes 11.2 megabytes in some sample of data that we took, gigabyte collection. If you start using the pointers to every single term, then you can squeeze it to just 7.6 megabytes. If you add on top of that you skip the pointers and only have it, in that case, we took 4. So every 4 terms, we have a pointer, but we add 1 byte with the length of the term. Then we are at 7.1. And then with the front coding, because of the alphabetical list of terms, we are at 5.9. So that's nice because we basically almost doubled what we can store in the same amount of memory, right? We halved the size of the vocabulary, and we double what we can store in working memory, right? So this is really beneficial. Now I skipped a few slides because I didn't want to lose my flow. But what I want to say is that this has a price. The moment you start compressing data, you will need the CPU to do more computations. So this has a price on the CPU. It means that it might take a bit more time for the CPU to decompress the data because it's much easier to read the terms if they are already stored exactly as they are in memory than it is to decode the front coding scheme with automatic, automata, automate, and so on. So it takes more time. But the benefit you get is that in exchange for it taking a little bit more time, you save space. And that is one of the major paradigms or principles in computer science, is that very often you have this space versus time spectrum, right? Either you are very fast or you take very little space. And then you can put the slider wherever you want. All right? So it's a compromise to make between the two. And what I wanted to also show you concretely in terms of compromise is the impact of having a pointer, not for every term, for the start and end of every term, but only every k terms, because that has an impact on the lookup of the terms. Because if you have a pointer at every term, you can use some sort of binary search, right, to know where they start and when they end, right? So if you compute the average memory seeks that you need, for example, if I have this structure, this is not an actual structure, but more like the showing you the number of seeks. If I'm lucky, I will already locate retrieval on the first go, but maybe I'm less lucky, and this one needs more memory seeks, right? And so you can compute the average number of seeks that you will get. In that case, it's 1.4. But now if you do have the less pointers and you have the length of the terms instead, then you will have a pointer that points to computer CPU data, and then the next one will be information retrieval Zurich, right? That's what I showed you before. But then there's no binary search anymore. Once you have arrived at a block of terms, then it's linear within that block of term, right? So in the worst case, the term you're looking for is at the very end, right? That's the last one. So in that case, there would be even 3 extra memory seeks. So you see here, it's now 1.7. So just to show you concretely that you can do calculations on how it's slowing you down, right? So basically, what I've just shown you is that I'm trying to do it not too fast to not flicker, going from here to here, make it slower. That was my first, where it's a perfect binary search, right? Perfectly balanced binary tree, going to these blocks of terms where now I'm slowing things down because if I'm unlucky, that could be the last term in my sequence. Who is with me? Right? Okay. So that's great. I'm going to jump directly here to avoid the flickering of the screen. So I think that's where I showed you the improvements. All right, so we are doing quite well, actually. A factor of 2 is nice. So that was the compression of the vocabulary, trying to compress the terms in less space. So we achieved a factor of 2. But now we have something that I find even cooler, that is the postings file compression. Because as a mathematician, this is really awesome, the sort of things that you can do in there, and with very impressive contributions by some people in the past. So we are done with that, and now we are going there. We are going to compress the postings list. Do you remember what a posting is? A posting is a pair term document, right? But because the postings that are on the same row all correspond to the same term, we don't repeat the term every time, right? We do it while we build the index. We've seen that. We've even been using term IDs to avoid the overhead. But once we have the standard inverted index, it's the same term all over the line. So basically we have here it's the posting information 1, information 2, information 4, information 5, information 8, information 9, but you already have information once and for all in here, and here we only store the document ID. What is the document ID? It's an integer. So a postings list, in fact, physically in the standard inverted index is a list of integers, right? So that's basically what it is. And now we have a mathematical problem, which is, how do we compress a list of integers? That is the mathematical problem that we are going to try to solve right now. So we can forget, in a way, about information retrieval and the standard inverted index and so on. We just try to squeeze lists of integers into as little space as possible in memory. So as always, we can start naively, right? If we don't try to compress at all, we could imagine that we are storing that as a linked list in our memory, and it's a linked list of, let's say, ints, right? An int would be 32 bits, so 4 bytes. So then you always need to do a quick calculation, right? 32 bits, what does it mean? That's 4 billion, right? You know how to compute powers of 2 very quickly, right? How I did 2 to the power of 32. You basically just need to keep in mind that 2 to the power of 10 is roughly 1,000. 2 to the power of 20 is roughly 1,000,000. 2 to the power of 30 is roughly 1 billion. So 2 to the power of 32 is 1 billion times 2 to the power of 2, right? So that who does these things already to very quickly compute powers of 2? It's good to train a little bit to be able to quickly do these approximations of powers of 2. So 2 to the power of 32, 4 bytes, gives me roughly 4 billion. 4 billion, that's quite a lot of documents, right? So we can do just fine with 4 billion document IDs, right? So that's 32 bits, and that means that I can allocate document IDs between 0 and 4 billion. I even put the exact values here, but of course nobody knows that by heart, right? So between 0 and 4 billion. That is if I'm using unsigned ints, right? If I'm using signed ints, then that would be between minus 2 billion and 2 billion. All right. Can we encode it with less space? Well, of course, the answer is yes, because otherwise there wouldn't be this lecture today, right? So I'm going to show you how we can encode it with less space. But there is first a very, very, very simple trick that we can start with. And that trick is about observing that postings lists are not just physically lists of any integers. They are sorted lists of integers, right? Because we allocate the document IDs increasingly, so we always have increasing integers. And that makes a difference, because that we can use, this information we can use to encode. Imagine I'm taking an example of a frequent term, quite a frequent term, and I have some part of the posting list here. It's longer than that, but I'm just showing a fragment of a posting list for a relatively frequent term. And we see that that term, whatever it is, appears in documents number 1056, 1058, 1063, 1064, and 1067. Can we do better than storing these 5 numbers as ints, as 44 bytes each? Yes? Absolutely. You can just store the difference. That is the trick. So that would be take a lot of space to do. But we can indeed, if we notice that these are small gaps, why don't we just encode the small gap, right? So for example, here we have gaps of 2, 5, 1, and 3, right? And so if we encode those gaps instead, so the first one, we still need to encode it as it is, but then the gaps can be encoded using less space, right? Who agrees with that? Right? We can just encode the gaps. So that's great. And so for the gaps, since the gaps are smaller, then we can just use less bytes, right? In that case, I'm just using 4 bits, and 4 bits is enough. It's half a byte, right? So it seems that we are doing very, very well at compression. But does anybody see the issue here? So, sorry, I didn't get that. Yes, exactly. The gaps here are a very specific case where they are very close to each other. So it's very, very small gaps, but that's because I took a frequent term. And if I take a term that is not so frequent, then I might have very large gaps, right? And the problem is that if I take, in that case, just 4 bits for the gap, that's only going to work for the frequent terms. It's no longer going to work for supercalifragilisticexpialidocious, right? That's not going to work there. So that's not it, right? We are not there yet. It's something we will use, but we cannot just do that with a fixed number of bits for the way we encode the integers. That's not enough, right? So it only works for the very frequent terms for which we really have very small gaps. And even for a frequent term, imagine that you have a collection that has 1 billion documents. You might have a frequent term that's going to appear in a lot of documents, but just because of the laws of large numbers, there might be very large gaps just randomly in between, right? You might have suddenly a gap of 30 documents without anything, right, in this super huge list. So that's not quite good enough, but still it's an idea that I'm taking because that idea might be useful for later, right? So we are going to indeed be encoding gaps in this way. But the one thing we would really need in here is what if we could store these integers in such a way that it's elastic? If it's small, it doesn't take a lot of space. And if I have a very large integer, then it elastically grows to take more space, right? So that would be ideal, right? If I just have this elasticity that the small integers don't take a lot of space and the very large integers can take more space. So can we have a variable gap size? Of course, as you guess, the answer is yes, and I'm going to show you how. And the first idea is to use a variable byte encoding. That's this first attempt at elasticity. But in order to make it elastic, we need to solve a problem that we've actually already seen with the terms somehow. It's the thing that if you have a fixed length for every integer, then you know exactly when they start and you know exactly when they stop, right? Imagine that we only have integers that take 4 bytes each. Then we know that the first 32 bits, that's my first document ID. The next 32 bits, that's my second document ID. If I want to look at the 10th document ID, that's very easy. It's a constant length every time. So I just multiply by 10, so 4 times 10, and I jump directly there. In fact, for those of you who know a little bit of C and C++, that's exactly how pointers and pointer arithmetics works in C++, right? When we have arrays or vectors or whatever, and whatever is in there always have the same length, then it's extremely efficient to look up data in there because you can instantly calculate the position in memory of every single member of your array. Who sees that? Right? But this is because we have a constant length and they're all stored on 4 bytes. Now, it means that even if I would give you like this, the sequence of bits, like you're really looking at the memory here, the actual memory, you know exactly that you read 32 bits, you read 32 bits, you stop here, then you read 32 bits and so on. So you have all the information you need to decode. But the problem is that if you have variable length and every one of these document IDs is stored on a different number of bits, for example, this one on 8 bits, this one on 16 bits, this one on 32 bits, 24 bits, 40 bits, 32 bits, and so on. Do you agree you no longer know when it begins and when it stops, right? Because if I just give you the bits like this, you do not have this information. That you don't know, right? You don't know which one has which length. So if I give you that, then you're lost. You have no idea when it's going to stop. Maybe it stops here, maybe it stops there, maybe it stops there. You just don't know because the length can vary every time. And this is why we have something that is called prefix codes. Who has ever heard of prefix codes? Who has never heard of prefix codes? Who has already used a phone? No more people than that, right? Don't scare me. Who has already used a phone? Almost everybody, right? Who has already used a landline phone? Have you noticed when you dial on a landline phone, so you have the tone that you pick up, you hear the tone, and then you start dialing the numbers, then the tone interrupts, then you dial, nothing happens, and the moment you're done dialing the number, let's say 10 digits, then it starts dialing. Now it seems like if it's always 10 digits, then that's easy, right? But not all numbers have 10 digits. The emergency numbers have 3 digits. And if you dial these 3 digits, it still starts dialing after just the 3 digits. It's not going to wait for 10 digits. That is because the phone number system uses prefix codes. It knows exactly when you're done dialing. And so I have a few examples here. For example, if you dial an emergency number, it will know that it stopped after 3 digits. If you dial, that's the entry point of ETH, that's 10 digits. And if you dial some number, in that case, it's California, so that is longer. But you have the 00 that says this is a number somewhere else, and 1 says it's North America, and so on. Internally, you have the same issue, right? You have, so the emergency numbers, at ETH, it's 5 digits for the internal phone system. And when you want to dial to the outside world, you need to add a 0 in front, right? And that's the case in many companies, that you need to add a 0, right? And that is because we need to make it a prefix code. This is the reason why we need to add that 0 in front. And so what happens, of course, nobody would do that, but if I actually would write phone numbers like this in a list and without telling you where they start and stop, who agrees you would be able to tell me when they start and stop? Right? It works because you just, if you know the phone numbering system, you can guess exactly when, not guess, you know exactly when they start and when they stop. And of course, the way it works is dependent on the country, right? Every country has their own rules for this. But the best example of prefix code that there is phone numbers. That's how to remember it. It's the phone numbers. And that's why an online phone knows exactly when to stop. For the smartphones, it's cheating, right? Because it directly ships the number to the server, and you don't actually have this tone or anything, right? You just click and it dials. But the landline phones make it very impressive. All right, so that is a prefix code. And in fact, we have another example of prefix code that you might know, which is UTF-8. In UTF-8, it's not always the same length for every character. It varies. So let me explain quickly how it works. Every character in UTF-8 has what is called the code point. it's basically a number, right? It's its number in the Unicode catalog. And the Unicode catalog is some standardization body that tells you which character has which code. That's called the code point, right? But a code point is really just an integer. It turns out that you often write these integers in base 16, hexadecimal format, but it's really just an integer, right? Now, you look at how large that integer is. If it's a small integer, and that's typically the case for ASCII symbols and the English Latin alphabet and so on, if it's at most 7 bits, then your UTF-8 encoding just puts these 7 bits after a 0. And that gives you the encoding. Now, if it's more than 7, but at most 10 bits, then what you do is you split it into 6 and 5, and you put 110 in front of the first 5 and 10 in front of the other 6, right? And then you have your encoded number that is basically made of these 5 concatenated with these 6. Now you see, this is where the elasticity happens, because here we have 8 bits, here we have 16 bits. But it works as a prefix code because this 110 that I see right here is telling me there are 2 packets. This 110 tells me exactly that. I just need to read that, and I know there's going to be 2 packets. And the 10 in here is a confirmation that this is another packet. Now, if I have a more recent symbol, like the euro, for example, at most 16 bits, then I need 3 packets. 1110, it needs to be different, right? That tells me there's going to be 3 packets. And then I have again this 10 that tells me this is a continuation packet, right? And now you see it's elastic, it grows. And that explains, by the way, why if you only have ASCII characters in a document that was encoded as UTF-8, but you open it as a text editor thinking it's ASCII, it will work because this actually matches exactly the ASCII encoding as well, if you only have these symbols. But if you try to open it as ASCII and it's not, and there's characters like this, then this is where you see the weird symbols. You've already seen that, right? You download some CSV file and it has umlauts in there and the umlauts don't appear and instead you have strange symbols. So that's because of this. All right, so this is again a prefix code. So we can draw some inspiration from here. You might notice that this might be a bit over-engineered for our purpose, of course, not for UTF-8. For UTF-8, it's very useful, but for us, that might be over-engineered because if you already know there's 2 packets, then why do you need to waste 2 bits for that, right? So in UTF-8, there is a reason for doing that. It has to do with the fact that if you just land in the middle of a document and you're lost, then you can use that as a hint to know where you are. So there is an algorithmic trick for which we're using that. But basically, what we need for our own purpose, for variable byte encoding for our own postings, is we can try with just 1 bit. The first bit in here, continuation bit, it's either a 1 or a 0. If it's a 1, that tells us this ends here. If it's a 0, that tells us it does not end here. So what's important is that you're not going to know in advance how many packets there are. Like here you do, because you can deduct it from the first bits in here. Here you don't know. You only know if you're done or not. And when you're done, you know it, right? So example, we encode the number 4. It has 3 bits. So we pad it with zeros all the way to 7. And we add a 1 in front. The 1 tells us it ends here. This is it, right? So this is the encoding of 4, right? Who is with me? Okay. So now we have a higher number that has more than 7 bits. Let's say 270, which happens to have the binary representation that you see here, 10001110. So what you do is you just try to count 7 bits brings us here, right? You just cut it here and rearrange like this, and you pad with zeros in here just to make it a multiple of 7. And then you put it nicely in 2 packets, and you have the 0 that tells us doesn't end right here. That's not the last packet. There's a few more packets after that. And the 1 that tells you, yes, now it ends here. Right, so we have this 1 bit that tells us yes or no, it ends here. Yes or no, do you have to continue reading more bits? That is called a variable byte encoding. Who would be able to encode any integer I give you with that pattern? Most of you, right? You write it in base 2, you group it in packets of 7, and then you pad with zeros to make it a multiple of 7, and then you add zeros to all the packets except the last one, and the last packet has a 1 in front. That's the general algorithm. Right. So it means that if I give you, for example, this number that actually is so large that I didn't even bother to give you the number in base 10, but let's say hypothetically, I found this, and I padded it with zeros to make it multiple of 7. Then I just put my bits in here, and I add a 0, 0, 0, 0 every time it doesn't end, and the 1 right here that says now it ends here. That is my general algorithm. Now, the example that I've shown you is specific to 8 bits as the packet size. Now, that's completely arbitrary, right? Why 8? Could be 4, could be 16, and so on. So could be any number of packets, right? And any size of packets. Imagine I take now a size of 4 instead of a size of 8. So it means that my packets now have 4 bits. It means 1 bit to tell me does it stop or does it not stop, and 3 bits that actually encode my number. So you see the smaller numbers that fit on 3 bits, they just appear as a 1 followed by the encoding. And then you see it elastically grows starting from 8, where now I have 4 bits. So I put these 4 bits now, I pad it with 2 zeros here to have 6. Then the 0 that says it doesn't stop here, and the 1 that says it stops here. And then you see the next jump will be at 64. At 64, now I have more than 6 bits. I have 7 bits, and now I need 3 packets, right? So you see this is a different encoding now with a size of 4, and you can take any size you want and make it work with that size. In fact, Unicode does exactly that because UTF-8 has the encoding with 8 bits, but there's also UTF-16 and UTF-32, right? UTF-16 uses packets of size 16, and UTF-32 uses packets of size 32. All right, and we save a bit of space that way, right? We are using actually less space. So if you look a little bit closer, you realize you can save half of the space. Right, but I'll quantify that a bit more when I get later to entropy and so on. We'll touch a bit information theory, but not just right now. All right, so far so good. Who is with me? Right, very good. Okay. There is a name for that kind of encodings that has a parameter, because the size of the packet is a parameter. That is called a parameterized encoding. A parameterized encoding means you cannot just go ahead and say, please give me the variable byte encoding of that integer. Then the person to whom you ask that is going to answer yes, but you need to give me the size of the packets, right? So you have parameters, and that can be 2 would be, so seriously, 2 would be ridiculous. But I mean 4, 8, 16, or even any integer that you want. Okay. And what's really nice is that this is a prefix code, because if I start looking at this sequence of bits that I just drew from my memory, and I don't tell you where it starts and where it ends, but I tell you this is a variable size encoding of length 8. Who is able to decipher that? Many of you, right? And indeed, you just reconstruct the packet, is size of 8. So every 8 bits is the continuation bit. And now I put them in red. So you see, now you know this one tells you it ends here. The one tells you it ends here. The one tells you it ends here. Oh, 0, 0, 1. So that is a very large number with 3 packets. 0, 0, and then it continues, right? So then I can simply decode by ignoring the leading bits. And that was 21, 95, 72, and so on. That is a list of integers, by the way. 21, 95, 72. I've just encoded a list of integers with variable size encoding. That's exactly what we wanted. We have this elasticity now that if it's a large number, it's going to take more space. If it's a small number, it's going to take less space. And now that you can combine with the encodings of the gaps. So you want to take the gaps between the document IDs, and with the gaps, you can use the variable byte encoding system. Who is with me? Okay, so you deserve the break. We're going to take 15 minutes of break, and then we'll continue with even better encodings than that after the break.